Close your eyes. Breathe slowly, deeply, calmly. Tonight, we're going on a journey through distances so vast that your mind will struggle to process them. We're going to explore the most unsettling truth about our universe, something that should keep you awake at night, but instead might just lull you into the deepest sleep you've had in weeks. We're talking about light years. You've heard the term before, probably hundreds of times. It sounds poetic, almost romantic. A light year. But do you really understand what it means? Not just intellectually, with numbers and calculations, but viscerally, in your gut, in that primal part of your brain that comprehends danger and distance. I'll tell you right now, you don't. And neither do I. Neither does anyone. Because the human brain, this incredible organ that can write symphonies and split atoms and contemplate its own existence, simply wasn't built to comprehend distances measured in light years. Let me paint you a picture. Imagine you're standing on a beach at night, looking up at the stars. You see Proxima Centauri, our nearest stellar neighbor, though you probably can't pick it out with your naked eye. It's sitting there 4.24 light years away. That sounds manageable somehow, doesn't it? Just 4 in a bit light years. 4 of something. But here's what that actually means.
If you could get in a car right now, a normal car, and drive at highway speed toward that star without ever stopping, never sleeping, never eating, never resting for even a single second, it would take you approximately 38 million years to arrive. 38 million years of driving without pause. That star, Proxima Centauri, is considered our closest neighbor. And here's what's truly disturbing about that fact. In cosmic terms, it's practically touching us. It's right next door. What lies beyond the distances separating galaxies, clusters of galaxies, superclusters, and the filaments of the observable universe? These are numbers so monumentally huge that the human brain simply collapses when trying to process them. We're not designed to understand these magnitudes. Our minds evolved to calculate the distance to the nearest tree, to know if a predator was too close, to understand how many days of walking separated us from the next river. But when we talk about light years, when we discuss distances where light itself, the fastest thing in the known universe, takes years, decades, centuries, or millennia to travel, our brains enter completely unfamiliar territory. And what you're about to discover on this journey will leave you speechless. First, we're going to understand why the universe uses time to measure space, something that defies all everyday logic. Second, you'll comprehend why every time you look at the stars, you're literally seeing the past. And not just any past, but ghosts of worlds that perhaps no longer exist. And third, we're going to explore the most terrifying implications of these distances, the real possibility that we're completely alone, trapped on a cosmic island from which we can never escape. If you're fascinated by the mysteries of the cosmos, subscribe. The journey begins now. When we were young in school, they taught us about the solar system in a rather gentle way. They showed us colorful diagrams where the planets orbited neatly around the sun, each at a comfortable distance from the others. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, all represented as little balls of different sizes and colors, floating on a black background with stars drawn as tiny bright dots. They made you memorize the order of the planets.
Maybe they told you some curious fact about Saturn's rings or Jupiter's great red spot. And with that, you considered the cosmos understood. The universe seemed like an orderly place, almost cozy. The stars were decorative points of light in the night sky, and space was simply the black void between them. But nobody explained the uncomfortable truth to you. Nobody told you that those school diagrams are completely out of scale, that if you wanted to draw the solar system respecting real proportions, you would need paper several kilometers long.
Nobody told you that the space between planets is so absurdly vast that it makes the planets themselves seem like specks of dust, lost in an infinite ocean of emptiness. And much less did they prepare you for what lies beyond the solar system. They left you with the comforting illusion that the universe was comprehensible, manageable, almost domestic. But the reality is much darker. The reality is that we live in a cosmos where distances are so grotesquely enormous that we need to invent completely new units of measurement just to be able to talk about them without going insane. And the most famous of these units, the light year, hides in its very name a truth that should make us tremble. Space is so incomprehensibly large that the only way to measure it is using time. Not kilometers, not meters, not any conventional unit of length. Time. The distance that light travels in an entire year. And light isn't exactly slow. It travels at 299,792 kilometers per second, not per hour, per second. In a single blink, light has traveled a distance equivalent to circling the Earth 12 times in 1 second. And yet, even traveling at that absolutely insane speed, light needs years to get from one star to another. It needs hundreds of years to cross our galaxy. It needs millions of years to reach the nearest galaxy. It needs billions of years to reach the edges of the observable universe. This isn't science fiction. This is the cold and calculable reality of the place where we exist. Let's start from the beginning, from the most basic concepts. Because to truly understand the magnitude of what we're discussing, we need to build the foundations step by step. A light year is, in simple terms, the distance that light travels through vacuum during one complete Earth year. Sounds straightforward, but when you do the calculations, the number you get is so absurd it seems pulled from the imagination of a novelist with delusions of grandeur. Light travels 299,792 kilometers every second. Multiply that by 60 seconds, and you have the distance it covers in a minute. Approximately 17,987,000 kilometers. Multiply that by 60 minutes, and you get the distance it travels in an hour. More than 1 billion kilometers. Now multiply by 24 hours, and you have the distance of one light day, approximately 25.9 billion kilometers. And finally, multiply by 365 days, and you get the light year, 9,460,800 million kilometers, 9.46 trillion kilometers. That's the basic unit that astronomers use to measure distances in the universe. And it's not even the largest one. There's the parsec, which equals 3.26 light years. There are kiloparsecs and megaparsecs for even greater distances. But let's stay for now with the light year, because it's already enough to make us understand how insignificant we are. To put this in perspective, let's think about something we can visualize.
The Moon, our natural satellite, is approximately 384,000 kilometers from Earth. Light takes a second and a half to cover that distance. When you look at the Moon in the night sky, you're seeing it as it was a second and a half ago. It's not a significant delay, it's practically real time. Now, let's go a bit further. The Sun is about 150 million kilometers from us. Light takes 8 minutes and 20 seconds to cover that distance. This means that if the Sun exploded at this precise instant, we wouldn't find out for more than 8 minutes. During those 8 minutes, we would continue seeing a bright and apparently normal sun in the sky, completely unaware of our imminent destruction. Already here, we begin to notice something unsettling. Even within our own solar system, there's a lag between reality and what we perceive. We don't see the sun as it is now. We see it as it was 8 minutes ago. But this is just the appetizer. Let's go further. Jupiter, the largest gas giant in our solar system, is at an average distance of 778 million kilometers from Earth. Light takes approximately 43 minutes to reach us from Jupiter. Saturn is even farther, at about 1.4 billion kilometers, and light needs about 80 minutes to make the trip. Neptune, the most distant planet in our solar system, is located about 4.5 billion kilometers away, and light takes more than 4 hours to reach us from there. And beyond Neptune, in the frozen confines of the solar system, we find the Kuiper belt and the hypothetical Oort cloud, regions where objects are so far that light can take days, weeks, or even months to reach us. But all this, absolutely all of this, is still within our solar system, still our immediate cosmic neighborhood. And yet, the distances are already so great that a message sent at the speed of light would take hours to reach the outer planets. The space probes we've sent to explore these worlds take years to arrive. Voyager 1, launched in 1977, took 12 years to reach Neptune. And Neptune is, cosmically speaking, just a step away from us. Now comes the truly terrifying leap. Let's leave the solar system. The nearest star to our Sun is called Proxima Centauri and is part of a triple star system known as Alpha Centauri. This star is 4.24 light-years away. 4.24 light-year. That means that light traveling at 300,000 kilometers per second needs 4 years, 2 months, and a few days to get from Proxima Centauri to Earth. The star you see shining in the night sky, if you could distinguish it with the naked eye, is not the star as it is now. It's the star as it was more than 4 years ago. If that star exploded tonight, we wouldn't know until the year 2029. For 4 years, we would continue seeing its ghostly light, not knowing that the source had already disappeared. And this is just the nearest star, the nearest one, our next-door neighbor in galactic terms. In kilometers, the distance to Proxima Centauri is approximately 40 trillion kilometers. 40 followed by 12 zeros. It's a number so large that it lacks intuitive meaning for the human brain, but let's try to give it some kind of context. If you could build a highway from Earth to Proxima Centauri and drive at 100 kilometers per hour without ever stopping, you would take approximately 45 million years to arrive. 45 million years of driving. By the time you arrived, humanity as we know it would have ceased to exist long ago. Entire species would have evolved and gone extinct multiple times during your journey. The continents of Earth would have changed shape and position. The sun itself would have aged noticeably, and you would still be driving, toward a star that perhaps isn't even there when you arrive. Because in 45 million years, many things can change. Stars move, stars die, stars explode. The cosmos is not static. It's an ocean in constant motion. And we are castaways on a tiny raft, trying to navigate toward an island that could sink before we get there. But perhaps the highway isn't the best analogy. Maybe we should use something faster. The fastest commercial aircraft in history, the Concorde, flew at approximately 2,180 kilometers an hour. If you could board a Concorde and fly directly toward Proxima Centauri without stopping, you would take more than 20 million years to arrive. Better, but still absurdly long. Let's try something more ambitious. The fastest object made by humans is the Parker Solar Probe, which reaches speeds close to 700,000 kilometers an hour when it passes near the Sun. At that speed, reaching Proxima Centauri would take approximately 6,500 years. 6,500 years. To put this in context, 6,500 years ago, humans were barely inventing writing. The pyramids of Egypt didn't exist. Stonehenge didn't exist. The wheel probably hadn't been invented yet. If our Stone Age ancestors had launched a probe at Parker's speed toward Proxima Centauri, that probe would be arriving approximately now. And that's using the fastest technology humanity has been able to create to date. But here's the catch. We can't send crewed ships at those speeds. We can't send ships with current technology that carry human beings to Proxima Centauri in a reasonable time. The best theoretical concepts, like solar sails, powered by lasers being studied in projects like Breakthrough Starshot, could theoretically reach 20% of the speed of light. At that speed, the trip to Proxima Centauri would take about 20 years. 20 years of travel for a tiny probe the size of a postage stamp that would send signals back that would take another 4 years to reach us. And that's assuming the technology works, that there are no problems along the way, that the probe survives the journey through the interstellar medium where cosmic dust particles at those speeds become devastating projectiles. For a crewed ship, a ship capable of carrying humans with everything necessary to survive for decades, the speeds would be much lower, the travel times much greater. Entire generations would be born and die aboard the ship before reaching their destination. And this is just to reach the nearest star, a single star, the neighbor next door. Now multiply that distance by the 100 billion stars estimated to be in our galaxy, the Milky Way, and you'll begin to glimpse the true scale of the problem. But before we get lost in galactic numbers, let's stay for a moment longer in our immediate stellar neighborhood. Because even here, in what astronomers call the solar neighborhood, the distances are enough to make you question everything you thought you knew about space. After Proxima Centauri, the next nearest star is Alpha Centauri itself, a binary system composed of 2 stars that orbit each other, located 4.37 light-years away. Then comes Barnard's star at almost 6 light-years. After that, Wolf 359 at 7.8 light-years. Land 21185 at 8.3 light-years. Sirius, the brightest star in the night sky, is 8.6 light-years away. And so we could continue listing stars increasingly distant until the numbers lose all meaning. But what's important here is to understand something fundamental. Within a radius of 10 light-years around the Sun, there are approximately a dozen star systems. 12 systems in a volume of space that encompasses more than 4,000 cubic light-year. That means the space between stars is mostly absolute emptiness. Nothing. Darkness. Cold. A void so deep it defies imagination.
Imagine you could shrink the sun to the size of an orange. A common orange, about 10 centimeters in diameter. At that scale, Earth would be a grain of sand orbiting about 10 meters away. Jupiter would be a marble at about 50 meters. Neptune would be almost 300 meters away. And Proxima Centauri, the nearest star, would be about 2,700 kilometers away. 2,700 kilometers. If the Sun were an orange in Madrid, Proxima Centauri would be another orange somewhere in Scandinavia. And between those two oranges, nothing but emptiness. Kilometer and kilometers of absolute nothingness. That's interstellar space. That's what separates one star from another. Even the stars we consider close are separated by chasms of void so enormous they're inconceivable to a human mind, accustomed to thinking in terrestrial distances. And here arises a disturbing question you may already be asking yourself. If the space between stars is so vast, so empty, so impossibly large, how could we ever explore it? How could we ever become an interstellar civilization? Science fiction has sold us the idea of spaceships that jump from one star system to another, like taking a flight from Madrid to Buenos Aires. It has accustomed us to thinking of interstellar travel as something possible, perhaps difficult, but achievable with the right technology. But reality is much crueler. The reality is that the laws of physics, as we currently understand them, impose brutal limits on our spatial ambitions. The speed of light isn't just a suggestion or a record to beat. It's a fundamental limit of the universe. Nothing with mass can reach it, much less exceed it. And even if we could approach it, even if we could build ships capable of traveling at 90% of the speed of light, interstellar journeys would still be enterprises of decades or centuries. Let's think about this calmly. Suppose humanity at some point in the future manages to develop revolutionary technology that allows travel at 90% of the speed of light. A ship like that could reach Proxima Centauri in approximately 4.5 years from the perspective of an observer on Earth. But the journey would have strange effects due to Einstein's special relativity. For the crew of the ship, time would pass more slowly. They would experience perhaps 2 years of travel while 4.5 passed on Earth. This is what's known as time dilation, and it's a real effect, experimentally verified, not science fiction. But even with these relativistic tricks, even shortening the subjective time of the journey, we would still face monumental problems. First, the amount of energy needed to accelerate a ship to 90% of the speed of light is absolutely colossal. We're talking about amounts of energy equivalent to the annual production of entire civilizations. The relativistic kinetic energy equation is relentless. The closer you get to the speed of light, the more energy you need to accelerate a bit more, and the amount grows exponentially. Accelerating a 1,000-ton ship to 90% of the speed of light would require more energy than humanity has produced in its entire history. Second, at those speeds, any particle of cosmic dust becomes a lethal projectile. A 1 milligram grain of sand, upon impacting a ship traveling at 90% of the speed of light, would release energy equivalent to several tons of explosive. The interstellar medium is full of these particles. A ship would need shields of a technology we can't even imagine to survive the journey. And third, there's the human problem. Even if we could build the ship, even if we could protect it, who would want to spend years or decades of their life traveling toward an unknown destination, knowing that when they arrive,
everyone they knew on Earth will have aged much more than them, or even died. Interstellar journeys, if they ever become reality, will be one-way trips, farewell journeys. The colonists who depart toward other star systems will never see Earth again, will never embrace their families again. They'll become voluntary exiles, castaways by their own choice, launching themselves toward the darkness of space with the hope of finding something on the other side. And that's just to reach the nearest stars, those that are a few light years away. Now, let's broaden the horizon. Our galaxy, the Milky Way, has a diameter of approximately 100,000 light years. 100,000 light years. To cross it from one end to the other, light needs 100,000 years. A ray of light that left from one end of the galaxy when Neanderthals still walked through Europe would be arriving approximately now at the other end. And light is the fastest thing that exists. Any ship we build, however advanced it may be, would take much longer. At Voyager speed, crossing the galaxy would take about 1.7 billion years. Even at the speed of light, it would be 100,000 years. That means that if an alien civilization sent a radio signal from the other end of the galaxy, that signal would take 100,000 years to reach us, and our response would take another 100,000 years to reach them. A simple conversation of question and answer would take 200,000 years. By the time we received their message and sent our response, that civilization could have evolved to be unrecognizable or gone completely extinct. Our galaxy contains between 100 billion and 400 billion stars, depending on estimates. Each of those stars is a sun, many of them with their own planetary systems. Data from the Kepler telescope and other missions suggest that most stars have at least one planet orbiting them. That means there could be more planets in our galaxy than stars. Trillions of potential worlds. And yet, due to the distances involved, the vast majority of those worlds will forever remain beyond our reach. We can observe them with telescopes. We can analyze the composition of their atmospheres through spectroscopy. We can speculate about whether they could harbor life. But visiting them, stepping on their surface, exploring their oceans and mountains, that's another matter entirely. Different. The center of our galaxy is about 26,000 light years away. There, in the heart of the Milky Way, is a supermassive black hole called Sagittarius A star, with a mass equivalent to 4 million suns. We will never see it directly with our own eyes. We will never send a probe to study it up close. It's so far that the light reaching us from that region departed when the first modern humans were beginning to leave Africa. When you look toward the center of the galaxy on a clear night, when you see that bright band of stars crossing the sky, you're seeing light that's thousands, tens of thousands of years old. You're seeing the frozen past, a ghost of how the galaxy was before any human civilization existed. And here we arrive at one of the most disturbing paradoxes of astronomy. The farther we look, the further back in time we see. This isn't a poetic metaphor, it's a physical fact. Light has a finite speed, and therefore information about distant events takes time to reach us. When you look at the moon, you see it as it was a second ago. When you look at the sun, you see it as it was 8 minutes ago. When you look at Sirius, the brightest star in the night sky, you see it as it was almost 9 years ago. And when you look at other galaxies, you see them as they were millions or even billions of years ago. This turns telescopes into time machines. We can't physically travel to the past, but we can observe it. We can see what the universe was like in remote epochs when Earth didn't yet exist, when the sun hadn't yet formed, when the first galaxies were being born from primordial chaos. The Andromeda Galaxy, our nearest galactic neighbor of comparable size, is 2.5 million light-years away. When you observe it through a telescope, or even with the naked eye on very dark nights, you're seeing light that departed from there 2.5 million years ago. Back then, our ancestors were primitive hominids, barely beginning to use stone tools. Homo sapiens didn't exist. Neanderthals didn't exist. Humanity, as we know it, was an impossible future to predict. And yet, that light, those photons that hit your retina when you look at Andromeda, began their journey at that moment. They've been traveling through space all that time, crossing the intergalactic void, surviving the expansion of the universe, only to end their journey in your eye at this precise moment in history. There's something deeply poetic and terrifying about that. But Andromeda, despite its seemingly impossible distance, is our nearest neighbor. It's part of what astronomers call the local group, a cluster of more than 50 galaxies that includes the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. The local group has a diameter of approximately 10 million light-year. 10 million light-year. That's the scale of our immediate galactic neighborhood. And the local group, in turn, is just a small part of the Virgo supercluster, a structure that spans 110 million light-year and contains at least 100 groups and clusters of galaxies. And the Virgo supercluster is just an appendage of an even larger structure called Lania, which means immense heaven in Hawaiian, and spans more than 500 million light-year. But not even Lania is the largest known structure. Astronomers have discovered cosmic filaments, walls of galaxies and voids that span billions of light-years. The Hercules Corona Borealis Great Wall, for example, is a structure 10 billion light-years in extension, one of the largest ever observed. And the observable universe in its entirety has a diameter of approximately 93 billion light-year. 93 billion light-year. That's the size of everything we can see, everything that light has had time to reach us since the Big Bang. And beyond the observable universe, there's more universe, perhaps infinitely more, that we can never see because its light hasn't yet had time to reach us.
And due to the accelerated expansion of the universe, perhaps it never will.
Here's where things start to become truly disturbing, because the universe isn't just incomprehensibly large, it's also growing. And it's not growing in a calm and measured way. It's accelerating. Every second that passes, the space between galaxies expands a bit more. Distant galaxies move away from us at increasingly greater speeds. And the most distant ones, those at the edges of the observable universe, are moving away at speeds that exceed the speed of light. Yes, you heard that right. Although nothing can travel through space faster than light, space itself can expand at any speed. And that's exactly what's happening. The fabric of reality itself is stretching, dragging galaxies with it like raisins in bread rising in the oven. And we're trapped on our tiny speck of cosmic dust, watching as the universe moves away from us forever. This phenomenon has devastating implications for any dream of cosmic exploration. There's a concept called the cosmological event horizon, not to be confused with the event horizon of a black hole. It represents the limit beyond which we can never receive information. Galaxies that are beyond this horizon are moving away from us faster than light can travel toward us. This means that any signal, any ray of light, any information they emit from now on will never reach Earth. They're disappearing from the observable universe forever.
And every year, more galaxies cross that threshold.
Every year, the accessible universe shrinks a bit more. It's as if we were on an island whose shore constantly recedes, leaving us with less and less ocean to explore. Currently, astronomers estimate we can observe approximately 2 trillion galaxies in the observable universe. 2 trillion, each with billions of stars, each star potentially with its own planets. The number of possible worlds is so large that any number you try to imagine falls short. But here's the cruel irony. Despite all that abundance, despite those trillions of galaxies and their countless worlds, the expansion of the universe is condemning most of them to disappear from our view forever. In about 100 billion years, when the sun has long since gone out and Earth is a distant memory, almost all galaxies will have crossed the cosmological horizon. The night sky will be empty. Any civilization that exists in that distant future will look upward and see only darkness, with no clue that there was once a universe full of light and wonders. But we don't need to go that far into the future to find terrifying limitations. Even now, with all our technology, with our space telescopes and our giant radio telescopes, there are galaxies we simply can't study because their light hasn't yet had time to reach us.
And there are others whose light did reach us, but
that show a universe so ancient, so different from the current one, that it's almost unrecognizable. The James Webb Space Telescope, for example, can see galaxies that existed when the universe was only a few 100 million years old. But those galaxies we see don't exist anymore. They're ghosts, frozen images of a past so remote that any civilization that could have existed in them would have had billions of years to evolve, expand, or go extinct. This leads us to an uncomfortable reflection on the very nature of astronomical observation. When we look at space, we're not seeing the universe as it is. We're seeing the universe as it was. And the farther we look, the further back in time we see. The universe we observe is a collage of different epochs, a mixture of near present and remote past superimposed on the same sky. The moon you see is a second away in temporal distance, the sun at 8 minutes, Proxima Centauri at 4 years, Sirius at almost 9 years, Betelgeuse, the reddish star in Orion's shoulder, is about 700 light years away, which means you see it as it was in the Middle Ages. The Orion Nebula is 1,300 light years away, showing you an image from when the Roman Empire still existed. The center of the galaxy is 26,000 light years away, revealing how it was when humans were beginning to paint in the caves of Altamira.
And when you look at other galaxies, the temporal leaps become truly dizzying. Andromeda, at 2.5 million light years, shows the universe when the genus Homo was taking its first steps in Africa. The Sombrero Galaxy, at 28 million light year, transports you to an epoch when the first apes were beginning to evolve. The Whirlpool Galaxy, at 23 million light year, is a window to a time when mammals dominated the Earth, but humans were an impossible future to predict. And the most distant galaxies we can observe, billions of light years away, show us epochs when Earth didn't even exist, when the sun hadn't yet formed, when the Milky Way was a young and chaotic structure, very different from the majestic spiral we know today.
This temporal perspective has a disturbing consequence for the search for extraterrestrial life. When we search for signals from civilizations on other stars, we're searching for signals from the past. If a civilization 1,000 light years away sent a radio signal toward us today, that signal wouldn't arrive until the year 3025. And any signal we're receiving now from that distance was sent 1,000 years ago, when that hypothetical civilization could have been very different from how it is now, or could even have gone extinct. Interstellar communication isn't just difficult because of the distances. It's difficult because it's communication across time. Any conversation with an alien civilization would be an exchange of messages between different epochs, with responses that would take decades, centuries, or millennia to arrive. This has profound implications for the Fermi paradox. That famous question that boils down to, if the universe is so big and so old, and if conditions for life seem to be relatively common, where is everybody? One possible answer, perhaps the most depressing, is that the distances and times involved make communication and contact practically impossible. Even if the galaxy were full of intelligent civilizations, even if there were millions of them, they could be so separated in space and time that they would never meet. They would be castaways on islands separated by oceans of light years, screaming into the void with no one able to hear them. Each civilization would be born, flourish, and die in its small corner of the cosmos, never knowing it wasn't alone. And here's the most disturbing truth of all. Even if we overcame all the technological obstacles, even if we developed ships capable of traveling at speeds close to light, even if we found ways to protect ourselves from radiation and particle impacts, we would still face a fundamental limit. The universe is simply too big to be explored in its entirety. No civilization, however advanced it may be, could visit all the stars in its own galaxy, much less all the galaxies in the observable universe. The time necessary would be greater than the life of the stars themselves, greater than the life of the universe as we know it. We are condemned to inhabit a cosmos of which we can only know an infinite decimal fraction, like ants on a beach trying to count every grain of sand in all the world's deserts. This limitation isn't technical, it's fundamental. It's not that we haven't yet invented the right technology. It's that the very laws of physics, the geometry of spacetime, the finitude of the speed of light, conspire to keep us locked in our small corner of the universe. We can look outward, we can observe the wonders of the cosmos through our telescopes, but we can never touch them. We can never visit them. They're so far, they might as well be in another universe, in another dimension, in another reality, completely separate from ours. And in a certain sense, they are. The observable universe is our accessible universe. Everything else, everything beyond the cosmological horizon, is as unreachable as the dreams we forget upon waking. Let's think for a moment about what this means for our understanding of the cosmos. Human beings have developed an astonishing capacity to observe the universe. We've built telescopes that can see galaxies billions of light years away. We've sent probes to all the planets in our solar system. We've walked on the moon. We've analyzed the chemical composition of planetary atmospheres tens of light years away. And yet, all this barely scratches the surface of what's out there. It's as if we had left our house for the first time, looked at the horizon, and understood that the world is infinitely larger than we ever imagined, and that we can never explore it all. But perhaps there's some comfort in this perspective. Perhaps the immensity of the universe, instead of making us feel insignificant should make us appreciate more what we have. We're here on this small blue planet, orbiting an ordinary star in the suburbs of an ordinary galaxy, and yet we've developed the capacity to wonder about our place in the cosmos. We've looked upward and understood, even if only partially, the magnitude of what surrounds us. That's extraordinary. That's almost miraculous. Of all the possible arrangements of atoms in the universe, of all the configurations of matter that could exist, this particular configuration, this collection of carbon and oxygen and nitrogen and hydrogen that we call humanity, has developed the capacity to contemplate its own place in existence. And as we contemplate that place, as we look at the stars and calculate the distances that separate us from them, something profound happens in our mind, something that goes beyond mere scientific curiosity. There's a connection, a sensation of wonder and humility that arises when we truly understand how small we are and how large the universe is. It's a feeling that our ancestors also experienced when they looked at the night sky. Although they didn't know the numbers, didn't know about light years or galaxies, they saw the same stars we see, the same points of light in the darkness, and felt the same mixture of wonder and terror before the unknown. The difference is that now we know more. We know those stars are distant suns, that many of them have planets, that some of those stars exploded long ago, and what we see is just a luminous ghost. We know the universe had a beginning, that it's expanding, that someday it will cool until it remains in absolute silence. We know we're made of the same material as the stars, that the atoms in our body were forged in the heart of suns that exploded before Earth existed. We're literally stardust that has developed the capacity to contemplate the stars. And that's perhaps the most beautiful and tragic irony of our existence. We're intelligent enough to understand how incomprehensibly large the universe is, but we're condemned to never be able to explore it. We can calculate the distances, we can measure them in light years, we can write the numbers in scientific notation and pretend we understand them. But deep down, those figures remain abstract, impossible to truly visualize. Our brain evolved to survive in the African savanna, to calculate the distance to the nearest tree, to know how many days of walking separated us from the next oasis. It didn't evolve to comprehend trillions of kilometers or millions of light years. Those scales are beyond our cognitive reach, as unattainable to our mind as the stars themselves are to our bodies. And yet, we try. That's perhaps the most admirable characteristic of our species. We know we can't truly comprehend cosmic distances, but we keep trying. We build analogies, create scale models, invent new units of measurement, all in an effort to get closer, even just a little, to understanding. It's an act of rebellion against our own limitations, an attempt to transcend the confines of our evolved mind and touch, even if only mentally, the edges of infinity. But no matter how much we try, there's always a point where comprehension stops and only wonder remains. A point where numbers lose meaning and only the overwhelming sensation of the vast, the ancient, the incomprehensible remains. And perhaps that's the greatest gift the universe offers us. Not the possibility of understanding it, but the opportunity to marvel at it, to feel small but conscious, to know that we're part of something immensely greater than ourselves, even though we can never know it in its entire. Let's return for a moment to something more tangible, something we can almost touch with imagination. Let's talk about the Voyager probes, those two small spacecraft we launched in 1977 and that now represent the human-made objects that have traveled farthest into the cosmos.
Voyager 1, in particular, has reached interstellar space, that vast ocean of void that exists between the stars. It's the first human object to leave the sun's bubble of influence and enter the true darkness of deep space. And when I say it has traveled far, I speak in human terms because in cosmic terms, it has barely moved. After more than 45 years of continuous travel, Voyager 1 is approximately 24 billion kilometers from Earth. 24 billion kilometers sounds impressive, and it is to us. But that distance represents barely 0.0025 light years, not even a thousandth of a light year. To reach Proxima Centauri, the nearest star at 4.24 light year, Voyager 1 would need approximately 73,000 years traveling at its current speed of 17 kilometers per second. 73,000 years. To put that in perspective, 73,000 years ago, Homo sapiens was just beginning to expand out of Africa. Agriculture didn't exist. Writing didn't exist. Cities didn't exist. Humans were small bands of hunter-gatherers struggling to survive in a hostile world. If our ancestors from 73,000 years ago had launched a Voyager toward Proxima Centauri, that probe would be arriving approximately now. And during all that time, during all the history of human civilization, from the first cave paintings to the invention of the internet, that small craft would have been traveling in silence through the void, crossing the darkness, approaching millimeter by millimeter to its destination. And when it finally arrived, if it arrived intact, it would find a star we barely know, with planets we've only glimpsed from afar. And the signal it sent back would take another 4 years to reach us. The message would say, "I have arrived." And by the time we received it, 73,400 years would have passed since launch. This is the reality of interstellar travel with current technology. It's not difficult. It's impossible on any timescale that makes sense for a human civilization. We can launch probes. We can send messages. We can point telescopes at the stars. But we can't go there. Not with chemical rockets. Not with ion propulsion. Not with any technology that exists today or is in development. The stars are so far, they might as well be on another continent of the cosmos, separated from us by oceans of void that no ship can cross. And here's where science fiction has done us a disservice. It has accustomed us to thinking of space travel as something like air travel. You board a ship, activate the engine, and in a few hours or days, you arrive at your destination. Movies and series show us ships that jump from system to system, like taking a connecting flight. But that's not science. It's fantasy. The reality is that even the most speculative technologies, those that only exist in the equations of theoretical physicists, would have brutal limitations. Antimatter engines, for example, could, theoretically, provide enough energy to reach significant speeds. But producing antimatter requires enormous amounts of energy, and storing it without it annihilating with ordinary matter is a problem we don't even know how to solve. Nuclear fusion engines, another favorite concept of science fiction, could offer better results, but we would still be talking about journeys of decades or centuries to reach the nearest stars. Project Daedalus,
A theoretical study conducted in the 1970s proposed a fusion-powered craft that could reach Barnard's star, almost 6 light-years away, in approximately 50 years. 50 years of travel for an unmanned probe, using technology we haven't yet developed to reach a star that's practically next door in galactic terms. And Project Daedalus was just a theoretical study. Building something like that would require resources that exceed everything humanity has ever invested in any project. But suppose for a moment we manage to overcome all these obstacles. Suppose at some distant future we develop ships capable of traveling at 10% of the speed of light. At that speed, Proxima Centauri would be 42 years of travel away. Sirius, the brightest star in the sky, would be 86 years. Vega, one of the nearest and brightest stars, would be 250 years. And the center of the galaxy, at 26,000 light-years away, would require 260,000 years of travel. Even at speeds that defy any imaginable technology, the distances remain crushing. The universe reminds us again and again that we weren't designed to conquer it. And yet, there's something beautiful about this attempt, something profoundly human in our refusal to accept these limits. Throughout history, our species has faced barriers that seemed insurmountable, and again, we've overcome them. We crossed oceans in fragile wooden vessels. We conquered the air with machines heavier than it. We walked on the moon barely 60 years after the first airplanes took off. We've demonstrated again and again that the limits of the possible are more elastic than they seem. But interstellar distances are of a different nature. They're not technological limits we can overcome with ingenuity and determination. They're fundamental physical limits written into the laws of the universe itself. The speed of light isn't a barrier we can break. It's the absolute limit of the speed at which any information, any object, any spacecraft can travel. Einstein demonstrated that accelerating any object with mass to the speed of light would require an infinite amount of energy. Not very large, infinite. And nothing can travel faster than light, because that would violate causality, would allow traveling backward in time, and create logical paradoxes that would make physics as we know it collapse. The speed of light isn't just a suggestion from the universe. It's the fundamental law that holds reality together. But even if the speed of light weren't a limit, even if we could travel instantaneously from one point to another in space, we would still face monumental problems. The universe isn't just big, it's also hostile. The space between stars is full of invisible dangers. Cosmic radiation, high-energy particles that constantly bombard anything that dares to venture outside the protection of a planetary magnetic field. On Earth, we're protected by our magnetic field in our atmosphere, which deflect and absorb most of this radiation. But in open space, an astronaut would be exposed to doses of radiation that would cause genetic damage, cancer, and eventually death. A journey of decades or centuries through interstellar space would expose crew members to cumulative amounts of radiation that no known shield can completely block. We would have to develop protection technologies that don't yet exist, or find ways to repair genetic damage in real time, something that's also beyond our current capabilities. And then there's the problem of the interstellar medium, that tenuous hydrogen gas and dust that fills the space between stars. At ordinary speeds, this medium is harmless. But at speeds close to light, each hydrogen atom becomes a high-energy projectile. A ship, traveling at 10% of the speed of light, would be bombarded by these atoms with energy equivalent to that of high-energy cosmic rays. Without adequate protection, the ship would be gradually eroded and the crew would be exposed to lethal radiation.
These are the problems rarely mentioned when we talk about interstellar travel. They're not as romantic as the shiny ships of science fiction, nor as exciting as hyperspace jumps. But they're real. They're the physical barriers we would have to overcome before even dreaming of visiting other stars. And so far, we have not the remotest idea of how to do it. But let's leave the technical problems aside for a moment and think about the deeper implications of these distances. Let's think about what it means for us as a species, as a civilization, as conscious beings lost in an incomprehensibly vast universe. If stars are so far, we can never visit them. If galaxies are separated by chasms of void that no ship can cross, then what are we? What role do we play in this infinite cosmos? Does our existence have any meaning? Or are we simply a chemical accident on a forgotten rock orbiting an ordinary star? These questions may seem too philosophical, too abstract for a documentary about cosmic distances, but distances and existential questions are intimately connected. When we truly understand how far the stars are, when we understand we'll probably never reach them, something changes in our perspective. Suddenly, Earth is no longer just our home. It's our only possible home. It's the only island of life and warmth in an infinite ocean of void and cold. And that should make us value it in a completely different way. Let's think about this. Earth's atmosphere is approximately 100 kilometers thick. Beyond that, space begins. The void, the cold, the radiation, death. Those 100 kilometers of breathable air, of adequate pressure, of tolerable temperature, are all that separate us from the abyss. It's a layer so thin compared to the size of the planet that, if Earth were an apple, the atmosphere would be thinner than the skin. And yet, that thin layer is the only thing that allows life as we know it to exist. It's our shield against the cosmos, our only refuge in a hostile universe. And beyond the atmosphere, beyond the moon's orbit, beyond the solar system extends the interstellar void. Billions of kilometers of absolute nothingness. Then perhaps another star with its own planets, and more void, and more stars, and more void, until the edges of the observable universe, 93 billion light-years of stars, and galaxies, and void mixed together in a cosmic dance we don't even begin to understand. And we here on our small blue rock, wondering if there's anyone else out there, wondering if we'll ever be able to know. The search for extraterrestrial life has been one of the great scientific projects of recent decades. We've pointed radio telescopes at the stars, searching for signals of intelligence. We've sent messages into space, hoping someone will hear them. We've analyzed the light from distant planets, searching for signs of atmospheres that could harbor life, and, so far, nothing. Absolute silence. The universe remains mute before our questions. This is what scientists call the Great Silence, and it's one of the most disturbing mysteries of modern astronomy. If the universe is so big, if there are so many stars with so many planets, if conditions for life seem to be relatively common, why haven't we found anyone? Why is the cosmos so quiet? There are many possible explanations, some comforting, others terrifying. Perhaps life is rarer than we think. Perhaps intelligence is even rarer. Perhaps civilizations self-destruct before they can communicate across the stars. Or perhaps simply the distances are so great that communication is impossible. Even if there were millions of civilizations in the galaxy, they could be so separated that they would never meet, each screaming into the void with no one able to hear. This last possibility is perhaps the most depressing, because it means we're not alone in the universe.
but we might as well be. It means there could be intelligent beings looking at the sky from distant planets, asking the same questions we do, feeling the same cosmic loneliness, and we would never know. The distances would condemn us to perpetual ignorance, to irremediable loneliness, to a silence that no signal can break.
There's a thought experiment that philosophers and scientists have used for decades to illustrate our cosmic insignificance. It's called the pale blue dot, and it arose from a real photograph taken by the Voyager 1 probe in 1990. When the craft had passed Neptune's orbit more than 6 billion kilometers from home, astronomer Carl Schorn convinced NASA to turn the cameras around and take one last photograph of Earth. The result was an image that has defined our cosmic perspective ever since. In that photograph, Earth appears as a tiny point of light, a speck of dust suspended in a ray of sun, barely visible, insignificant, lost in the immensity of space. Schorn wrote about that image with an eloquence that still moves us today. He said, that point was our home, our only home. That all human beings who have ever existed, all kings and peasants, all saints and sinners, all lovers and haters, have lived their lives on that speck of dust. All wars have been fought over a piece of that dot. All religions have proclaimed to have the truth about that dot. All of human history, from the first civilizations to the present, fits on that small blue pixel floating in the void. And here's what's truly overwhelming. That photograph was taken at only 6 billion kilometers. That's less than a light day away. 0.006 light year to be precise. If Earth looks so insignificant from that distance, imagine how it would look from Proxima Centauri at 4 light-year. It wouldn't be visible at all. It would be completely invisible, lost in the glare of the sun, which in turn would be barely another star among many in the night sky of that distant world. And from the center of the galaxy, at 26,000 light-years, the sun itself would be invisible to the naked eye, one among billions of stars with nothing to distinguish it from the others. Earth wouldn't even be a concept. It would be less than nothing, a statistical impossibility in an ocean of possibilities. This perspective can be devastating if we look at it from a certain angle. It tells us that everything we consider important, everything we value, everything we fight and die for, occurs on a stage so small that the universe doesn't even notice. We could disappear tomorrow. The sun could swallow Earth, and the cosmos would continue its eternal dance unmoved. Galaxies would keep spinning. Stars would keep being born and dying. The universe would keep expanding toward its final destiny of cold and darkness. And no one, absolutely no one beyond our solar system would know we ever existed. But there's another way to look at this perspective, a way that paradoxically can be a source of comfort and wonder. Because if we're so small, if our existence is so brief and so fragile on the cosmic scale, then the simple fact that we're here, that we're conscious, that we can contemplate the universe and wonder about our place in it is something extraordinary. We're the universe trying to understand itself. We're matter organized in such a way that it can reflect on its own existence. In an apparently indifferent cosmos, we've emerged as islands of meaning, of purpose, of consciousness. And when we look at the stars, when we calculate the distances that separate us from them, when we feel that vertigo before the incomprehensibly large universe, we're experiencing something profound. We're brushing against the limits of what our evolved brain can process. We're peering into the abyss of infinity and feeling, even if just for a moment,
the true scale of reality. Few beings in the history of the universe have had that privilege. Few atoms have organized themselves in such a way that they can do that. But let's return to distances, because we haven't yet explored all their implications. We've talked about nearby stars, about our galaxy, about the observable universe. But there's something more we must consider: deep time. Because cosmic distances don't just separate us in space, they also separate us in time. And when we look toward the edges of the universe, we're looking toward the most remote past, toward epochs so ancient they defy any notion of human history. The universe is approximately 13.8 billion years old. That's its estimated age, calculated from observations of the cosmic microwave background, the residual radiation from the Big Bang that still permeates the entire cosmos. 13.8 billion years. To put that number in perspective, if we compressed all the history of the universe into a single calendar year, the Big Bang would have occurred in the first second of January 1st, and humanity would have appeared in the last seconds of December 31st. All our history, from the first civilizations until today, would fit in the last second of that cosmic year. We're latecomers to a party that's been going on for billions of years. And when we look at the distant universe, we're seeing that party in its early stages. The most distant galaxies we can observe emitted their light more than 13 billion years ago, when the universe was young and chaotic. Those primitive galaxies were very different from those we know today. They were smaller, more irregular, more violent. The stars they contained were first generation, formed from the primordial hydrogen and helium that emerged from the Big Bang, without the heavier elements that are now so common. The carbon in our bodies, the oxygen we breathe, the iron in our blood, none of those elements existed in those primitive galaxies. They were created later in the heart of stars that lived and died to seed the cosmos with their ashes. This means that when we observe those distant galaxies, we're seeing a universe where life as we know it was impossible. There were no rocky planets like Earth, no liquid water, no complex organic chemistry. The cosmos was a sterile and violent place, full of radiation and stellar explosions, but empty of any conscious observer. Billions of years passed before the universe became quiet enough, rich enough in heavy elements, mature enough for life to emerge. And when it finally emerged, it did so in this small, forgotten corner of an ordinary galaxy, on a planet orbiting a middle-aged star, in an epoch that's barely an instant on the scale of cosmic time. The coincidence of being here at this particular moment in the history of the universe is extraordinary. If we had emerged too early, the cosmos wouldn't yet have had the elements necessary for life. If we emerged too late, the stars could have gone out, leaving only white dwarfs cooling and black holes wandering in the darkness. We exist in a specific temporal window, a relatively brief period in the life of the universe where conditions are adequate for the existence of conscious beings. Cosmologists call this the stelliferous era, and it will last perhaps another 100 trillion years before the last stars go out and the universe enters its long, final night. But a 100 trillion years, though it sounds like an eternity, is just an instant compared to what comes after. When the stars go out, the universe will enter an era of darkness that will last much, much longer. Black holes, the only objects that will remain, will slowly evaporate through a process called Hawking radiation. But that evaporation will take time. So long, they make the current age of the universe seem like a blink. A black hole, with the mass of the Sun, would take 10 to the 67th power years to evaporate. A supermassive black hole, like the one at the center of our galaxy, would take 10 to the 100th power years. Those numbers are so large they have no intuitive meaning. They're durations that make eternity itself seem short. And after the last black holes evaporate, the universe will continue to exist, but it will be a completely different place from what we know. It will be a cold and dark void, without stars, without planets, without organized matter. Only scattered particles moving away from each other forever in a space that continues expanding eternally. Some physicists call this state the heat death of the universe, the final destiny of everything that exists, a perfect equilibrium where nothing happens, where nothing can happen, where time itself loses meaning because there are no events to mark it. This is the destiny that awaits us. Not us personally, of course, not even our species or our civilization, but the universe as a whole. Everything that exists, all galaxies and stars, all planets and moons, all forms of life that may arise in any corner of the cosmos, are destined to disappear into that final void. It's a perspective that may seem depressing, but it also has a certain dark beauty. It reminds us that everything is temporary, that even the universe itself has an expiration date, that nothing, absolutely nothing, lasts forever. But let's return to the present, because we still have billions of years before the stars start going out. We still have time to explore, to wonder, to marvel. And the questions that arise from cosmic distances are some of the deepest we can ask ourselves. Are we alone in the universe? Are there other minds contemplating the same stars as us, asking the same questions? Will we ever be able to find them, communicate with them, know that we're not alone? The search for extraterrestrial intelligence, known as SETI, has been listening to the sky for decades, searching for artificial signals. Giant radio telescopes sweep radio frequencies, searching for patterns that can't be explained by natural phenomena. So far, as we've mentioned, the result has been a disturbing silence. But that doesn't mean we're alone. It could simply mean that the distances are too great, the signals too weak, the time too short. Let's think about this. Humanity has been emitting radio signals into space for barely a century. That means our technological presence has only had time to reach stars within a radius of 100 light years. A radius of 100 light years around the Sun contains perhaps about 15,000 stars. 15,000 out of 100 billion stars in the galaxy. Barely an infinite decimal fraction. And our first radio emissions were weak, scattered, barely distinguishable from cosmic noise. The chances that someone has detected them and has had time to respond are extremely low. And then there's the question of time. Civilizations aren't eternal. They emerge, flourish, and eventually disappear, whether from natural catastrophes, self-destruction, or simply evolution into something different. If an average civilization lasts, say, 10,000 years as a technological civilization, then the window for communication is very narrow. We would need that civilization to exist at the precise moment of our history, close enough for signals to arrive in both directions, and with the adequate technology to detect and respond. The odds are overwhelmingly low, not because life is rare, but because the universe is too big and time too deep. This is the true tragedy of cosmic distances. They don't just separate us in space, they also separate us in time. There could be civilizations that flourished millions of years ago in distant galaxies, but by the time their light reaches us, they'll have disappeared eons ago. There could be civilizations that will arise in the distant future, but we won't be here to know about it. Each civilization is an island in space-time, shining briefly before going out, never knowing who else shared the cosmos with it. But perhaps there's another way to see it.
Perhaps the fact that distances are so great, that time is so deep, that communication is so difficult, makes us appreciate more what we have. We're here now, at this precise moment in the history of the universe. We can look at the stars and wonder about them. We can build telescopes and send probes and calculate distances. We can imagine what lies beyond the horizon, even though we can never reach it. And that in itself is extraordinary, because the universe doesn't need to be understood, doesn't need observers, doesn't need anyone to calculate its distances or marvel at its immensity. It could perfectly well exist, empty of all consciousness, a dance of matter and energy with no one to witness it. But here we are, small, fragile, ephemeral, wondering, marveling, bearing witness to something infinitely greater than ourselves. And in that act of contemplation, something magical happens. The universe, through us, becomes conscious of itself. The atoms that make up your body were forged in stars that exploded billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of that came from ancient supernovas, from stellar cataclysms that occurred before the sun existed. Those atoms traveled through space, condensed in a gas cloud, formed the solar system, organized into a planet, and eventually became you. You're literally stardust that has developed the capacity to contemplate the stars. You are the universe looking at itself in a mirror of consciousness.
And when you feel vertigo before cosmic distances, when you get dizzy trying to understand what a light year means, when your mind collapses before the impossible numbers of kilometers and billions and trillions, you're experiencing something profound. You're brushing against the limits of what your evolved brain can process. You're peering into the abyss of infinity and feeling, even if just for a moment, the true scale of reality. Few beings in the history of the universe have had that privilege. And so, we arrive at the end of this journey. Although in reality, no journey through the cosmos has a true end. There's always more space to explore, more distances to calculate, more questions to ask. But before closing, I want us to stop for a moment to reflect on everything we've covered together, on what it means to live in the universe where distances are measured in light years, on what it implies to be conscious of our own cosmic insignificance, on the weight of knowing we'll probably never reach the stars that shine over our heads every night. We've talked about light traveling at 300,000 kilometers per second, the maximum speed allowed by the laws of physics. We've calculated that even at that impossible speed, crossing our galaxy would take 100,000 years. We've imagined space probes traveling for millions of years towards stars that might no longer exist when they arrive.
We've contemplated an expanding universe where distant galaxies move away from us faster than light can pursue them, disappearing forever beyond our observable horizon. We face the possibility that we're alone, not because there's no life elsewhere, but because distances make any meaningful encounter impossible. All this may seem depressing, may feel like a condemnation. We're trapped on our small blue rock, looking toward an ocean of stars we can never reach.
We're castaways on a cosmic island, screaming into the void without hope of answer. And yet, there's something profoundly liberating in accepting this reality. Because when you stop fighting against the limits of the universe, when you accept that some things are simply beyond your reach, you can begin to appreciate what you do have. You can begin to value this small speck of dust we call home. Earth is a statistical miracle, a planet at the perfect distance from its star, with just the right mass to retain an atmosphere with liquid water on its surface, with a magnetic field that deflects lethal radiation from space. For more than 4 billion years, this small world has harbored life. From the first cells to the incredible diversity of beings that inhabit it today. Forests that breathe, oceans teeming with creatures, skies crossed by birds and clouds, and in some corner of this biosphere, a species that looks upward and wonders what's beyond. Every time you contemplate the night sky, you're participating in a tradition as ancient as humanity itself. Our ancestors looked at the same stars, though they gave them different names and told different stories about them. Ancient navigators used the stars to guide themselves across unknown oceans. Priests of lost civilizations studied the movement of celestial bodies to predict seasons and eclipses. Greek philosophers speculated about the nature of those luminous points, wondering if they were distant fires or holes in the celestial vault that let the light of the beyond shine through. Each culture, each generation has looked upward and felt that mixture of wonder and smallness you feel now. But we know something they didn't know. We know what those lights in the sky really are. We know they're suns, many of them larger and brighter than ours, some surrounded by planets that could harbor life. We know how far they are, although those distances defy our comprehension. We know the universe is immensely larger than any ancient civilization could have imagined, and that we're immensely smaller than any human ego would want to admit. That knowledge is a gift and a burden, a privilege and a responsibility. Because knowing how fragile we are, how isolated we are, how ephemeral our existence is on the cosmic scale should change the way we live. It should make us more humble, more compassionate, more aware that this small planet is all we have. There's no planet B waiting to be colonized. There's no alien civilization that will come to save us from ourselves. We're alone here on this floating island in the void, and what we do with it will determine the fate of the only life we know exists in the entire universe. The wars we wage, the borders we draw, the conflicts that divide us, all of that loses meaning when you look at it from the cosmic perspective. From Proxima Centauri, there are no countries. From the center of the galaxy, there are no races or religions. From Andromeda, Earth itself is invisible, a grain of dust orbiting a forgotten spark. All our differences, all our disputes occur on a stage so small that the universe doesn't even register it. We're a divided family fighting over the rooms of a house that floats alone in an infinite ocean. And while we fight, the house deteriorates, resources are depleted, and outside there's no one who can help us. This perspective doesn't intend to make you feel bad. It intends to make you feel connected. Connected with every other human being who shares this planet with you. Connected with every form of life that has evolved here over billions of years. Connected with the cosmos, of which we're all temporary manifestations. The calcium in your bones and the iron in your blood come from stars that exploded before the sun was born. The atoms in your body have been part of countless beings before you and will be part of countless beings after. You're a temporary pattern in the eternal flow of matter and energy, a moment of consciousness in a universe that mostly lacks it. And when that moment ends, when the atoms that compose you disperse and reorganize into other forms, the universe will continue. Stars will keep being born and dying. Galaxies will keep colliding and merging. Space will keep expanding. And perhaps, in some distant future, other beings will contemplate the cosmos and ask the same questions you ask now. Perhaps they won't be human. Perhaps they won't even be carbon-based, but they'll feel the same wonder, the same smallness, the same connection with something infinitely greater than themselves. That's the heritage we leave to the universe, not our buildings or our machines, which will turn to dust long before the stars go out, but our curiosity, our capacity for wonder, our will to look toward the unknown and wonder what's there. Those qualities, if they manage to be transmitted to future generations, could survive much longer than any stone monument. They could inspire civilizations yet unborn to keep exploring, keep asking, keep marveling. And meanwhile, while we're here, we can enjoy the show. We can go out on clear nights and look upward, knowing that each point of light is a sun. We can read about the probes we've sent to explore our solar system, those small emissaries of human curiosity traveling toward the void. We can follow the discoveries of space telescopes that every year reveal new worlds, new wonders, new unanswered questions. We can do all this knowing we'll probably never get there, but that the journey of knowledge is valuable in itself. Because in the end, that's what defines us as a species. Not our capacity to conquer, but our capacity to wonder. Not our power, but our curiosity. We've looked at the sky since we had eyes to see, and we'll keep looking as long as someone exists who can do it. The stars are too far to reach with our hands, but they've never been too far to reach with our imagination. And that imagination, that capacity to dream of the impossible, is perhaps the greatest gift the universe has given us. So the next time you look at the night sky, remember what you've learned today. Remember that those points of light are at incomprehensible distances. Remember that the light you see departed from them years, decades, centuries, or millennia ago. Remember that each star could have planets, and each planet could have stories we'll never know. Remember that the universe is so big, our words aren't enough to describe it, and so ancient that our history is barely a blink in its existence. But also remember this: you're part of all that. The atoms that compose you are as ancient as the universe itself. They've been traveling, transforming, reorganizing for almost 14 billion years. And now, at this precise moment, they've organized in such a way that they can contemplate the stars from where they came. That's extraordinary. That's almost magical. In an apparently indifferent cosmos, you've emerged as a spark of consciousness capable of wondering about your own origin and destiny. Light years will continue to be distances our mind can't truly comprehend. We can write the numbers, we can do the math, we can build models and analogies, but deep down, those magnitudes will always exceed our capacity for visualization. And perhaps that's okay. Perhaps we don't need to understand them to appreciate them. Perhaps it's enough to know they're there. Those immensities that surround us, those chasms of space and time that frame our small existence. Because, in the end, what matters isn't how much of the universe we can know, but how much we can marvel at it. It's not how many stars we can reach, but how much we can appreciate the ones we see from here. It's not how long we live, but how conscious we are of being alive. And in that sense, cosmic distances aren't a barrier, but an invitation. An invitation to humility, to wonder, to reflection on our place in the grand scheme of things. The universe owes us nothing. It didn't promise us it would be comprehensible or reachable, or that it would make sense. It simply is, vast and indifferent, beautiful and terrible.
And we have the privilege of contemplating it during the brief instant that our existence lasts. That in itself is more than we could have asked for. That in itself is enough. So let the distances overwhelm you. Let the light years make you feel small. Let the silence of the cosmos wrap around you like a blanket as you close your eyes and prepare for sleep. Because tomorrow, the sun will rise again. That ordinary star that is our source of life. And you'll have another day to marvel at the universe. Another day to ask unanswerable questions. Another day to be conscious of being alive in a cosmos that mostly isn't.